Hi everyone and welcome to the ZDResearch exploitation course. Every course needs some pre-requirement knowledge, and exploit development also needs some pre-requirement. So to continue the next onto the next chapter and learning the concept of exploit development, you should know some basic knowledge of Windows operating system. You don't need to be a master of Windows internal, but you should know about kernel mode and user mode, process, threads, and PE file format and segments. These are some pre-requirements you should know about it. And if you are going to, for example, exploit some other operating system, you should know some knowledge of that operating system. And besides some operating system knowledge, you should also know the basics of C programming language or C++, no difference, and some X86 Assembly syntax. You don't need to be able to write assembly program, but you should know you should be able to understand assembly syntax when used encounter with some binary code. In this course we use some debuggers and disassemblers. Of course there may be some other tools like X86 or some other editors, but disassembler and debugger are our main tools, so you should know about Immunity Debugger or WinDBG and famous IDA disassembler. In this chapter, I'm going to review some of these pre-requirements. So for experienced people know about reversing or low-level programmers, this chapter is these people can skip this chapter or skip it or review it so fast. And we are going to talk about some operating system concepts, X86 assembly, and reviewing our lab and debugging and assembling. We are going to show you our lab that we will use in the next chapters in the real exploitation things. Windows operating system separated into two main mode as kernel mode and user mode. Kernel mode uses the upper 2 GB of memory address as indicated here, and it's a privileged mode. It means that when you are in kernel mode you can do everything with the system, with personal computer or any kind of computer. You have the complete power of hardware. You can have direct I/O with ports and everything. Kernel mode is dedicated to operating system code and structures, and also, of course, the drivers that need to operate directly to hardware. And this critical section, the kernel mode, the whole kernel mode, is protected from user mode. So user mode programs cannot help the system or do bad things to the internal operating systems by default. They cannot directly modify file system and such things. And we have another mode, user mode. User mode uses the lower 2 GB virtual memory address. Later I will talk about what is virtual memory, and it's used the lower memory. User mode is a kind of non-privileged mode. It means that user mode applications running in user mode cannot have access to the operating system structure, to the drivers or something. And this mode of operating system, this mode of execution is dedicated to user applications. For example, when you install some browser application, Chrome browser, Firefox browser, these applications are installed in user mode, so they don't have to so we are less worried about their behavior. But user modes should communicate with kernel mode, and the way user mode communicates with kernel mode is by the help of some user mode APIs that use the syscalls to communicate with kernel mode. For example, when you are calling create process from kernel 32 library, create process call the NTDLL library NTCreate process, and NTCreate process do the job of process creation by help of a syscall to the kernel. This picture is grabbed from the Windows internal books, and here you can see the concept in this image. As you can see, various applications, Task Manager, Explorer, and other user applications communicate with the kernel mode through the NTDLL modules. And there are, of course, various subsystems and DLLs for other things. And the NTDLL communicate to the kernel mode by the help of System Service Dispatcher. I previously mentioned some syscalls. Syscalls actually uses this System Service Dispatcher to communicate with various kernel components. Well, process. Every program can have some number of processes. So you should know conflict process with a program. A process is not a program. A program is a sequence of bytes, a sequence of code that runs through the CPU. But process is a logical separation that have some characteristics and attributes, and that we are going to talk about it. And every process has its own virtual memory address. It means that when you spawn a new process you can see it in your Task Manager Windows. When you spawn a new process, this process has its own virtual memory address, its own virtual view of the memory. So in this way, various processes don't have access to other for example, process A don't have access to the memory of process B. And process also also is the owner of some system objects. For example, when you are creating a file with the help of create file API, you will create a file object, and it will be stored in kernel. The file object has an owner, and the owner is the creator of that file object. And there are also other objects, file, mutex, thread, token, and process, or other things. And every process has at least one thread of execution. So the execution code would not be belong to the actual process. It's belonging to a thread, and that thread is belonging to the process. And what is thread? Every process has one or more thread of execution. And when you, for example, write a simple C program, the main function uses the main thread of execution. And you can create more threads for other tasks. So the multi-threading architecture works this like. And every thread has its own CPU context. As I mentioned before, every process has its own virtual memory address, and every thread has its own CPU context. It means that every thread sees all the CPU components for itself. For example, we don't have 1,000 number of EX register physically, but we have an EX register for every thread. So because this behavior is called context, and when CPU switch between various threads, this process is called context switching. And every thread has two stacks, a user mode stack and a kernel mode stack, and we will show you later in our lab that you can see stacks of some threads in the debugger. What is virtual memory? As I mentioned before, there are lots of virtual memory in a running operating system, one per any running process. So every running process has its own virtual memory. Virtual memories are some kind of virtual view of memory for that process. Virtual memory is not exist physically. So how a program, a process works with the actual physical memory. The operating system actually mapped the virtual memory to the equivalent physical memory. When some data is needed to read it from that virtual memory, that data is mapped to the physical memory and read by CPU. And when the data in that virtual memory of a process is not needed anymore, the concept of paging would happen. Paging means that the unneeded data that a process is the owner would be mapped into the disk for temporary, and later would be back to the physical memory when needed. Virtual memory stores various type of data. Here we have some category of such data that a virtual memory of a process can contain. Mapped executables, dynamic allocations, a stack of threads, and mapped files. Mapped executables are actually the executable and modules that some program is going to run, and they mapped exactly in this as they are to the memory, to the virtual memory. And dynamic allocations are some allocations that can be allocated with various APIs through the operating system, with the virtual memory API or some kind of heap allocator. And Windows operating system has a default heap allocator. That's most of the programs on Windows use this heap allocator, but there are some programs that, because of some interoperability on performance reason, uses their own heap allocator, like browsers. And every virtual memory has some memory for stacks. Each thread has a user mode stack. So when you see a memory of some process, you see various stacks for various threads. And mapped files can be used, for example, in inter-process communications. Here we mentioned required knowledge for starting the exploit development course, but you can learn more of such stuff in Windows internal book. And Windows internal book is a very helpful book for some Windows hackers, because you need more knowledge when you encounter some other problems. But we are not going to explain the whole Windows internal in this course, so this introduction was enough for the operating system things. And in the previous slide, I mentioned the mapped executable. Mapped executable is the exact copy of the portable executable, PE, in memory. PE is a file format that Microsoft used for the executables in Windows operating system. And this is the reason PE files, exe files, will not be run in other operating system by default without any emulation. The full file format of the PE file is documented in the following Microsoft link in the following specification, and you can learn more about it. But one of the important things you should know about PE is that every PE file, every executable file has some sections. Common sections and important sections that every executable file has is a text segment, data segment, and BSS segment. Text segment is reversed for the actual machine instructions. So the instructions of some binary program is placed in the text segment of that module, and the data section is dedicated to initialize data. For example, when you set some global variable for some string type, this string will be initialized in this section and is statically compiled to this section. And BSS section is for uninitialized data, and most of the time when you open a module in a IDA disassembler, you see that it has some BSS section and it's empty. And here you can see a view, an overview of some PE file, DOS header, PE signature, COF header. You don't need to know exactly about PE for exploitation, but if you know more about it, it would be helpful in some problems of your work. Let's go through the X86 assembly. X86 assembly is the language of, can be called as language of Windows exploit developer. So any Windows exploit developer should know about this language. For other exploitation purpose, for example, you are going to exploit some iPhone cell phone. iPhone has another architecture is use ARM. So in that purpose, you should know the ARM assembly. But for the personal computers, X86 is proper. Before going through the instructions and the format of X86 assembly languages, you should know about registers. Registers are some type of fast memory that is embedded into the microprocessor. Registers are used because of performance and is a very fast memory. So CPU has not to read always from the physical memory. It can sometimes use this register for faster computation. And we have various registers in a CPU, and for various CPU models would be some different registers, but there are some main registers that every X86 CPU should support. So, and some of them are more important for our purpose of this course. There are 8 general purpose registers called EAX, EBX, E6, EDX, ESI, and so on. And flag registers for storing various flags, and an EIP register. As you see, all of these registers are prefixed with the E letter. This is the reason that the backward compatibility for the previous 16-bit system that used to be uses AX, BX, CX register. So this register is a kind of extended register to 32-bit platform. General registers can be used for any reason in the machine code. But, and you can see here the general registers, they can be divided, some of them can be divided to various smaller registers. For example, EAX, EBX, E6, EDX can be used as 16-bit register as IX, BX, 6DX, and in this case we just use the lower part of that register. And when we are going to use just 1 byte of that register, we will use a smaller separation, AL, BL, CL, and AH, BHDL. You can see this concept in this view. Of course, there are just 4 registers available for this kind of separation. And one important other concept for every reverse engineer or exploit developer is that these are called general purpose registers, but compilers, most of the time, the Visual Studio compilers from Microsoft, and most of the compilers use these registers for some special usage. For example, EX register is always used as the return value for functions. So as a reverse engineer, you should know that when you are debugging some function, the return value is stored finally as in EX register. So you should track EX register when you are going to finish that function. And ECX register is, for example, is used for counters most of the time. When you write a loop, a for loop, for example, compiler most of the times use the ECX register as the counter. Of course, ECX register has another special usage in object-oriented code that we will cover in some later chapters for storing the disk pointer. EDI register is used for the destination index in string operations. For example, when you use the instruction STOS, that is a string instruction, it uses the EDI register as the destination address, as the destination of copying the instruction, the string. And ESI is the opposite of EDI, can be considered as opposite of EDI in this kind of usage as the source index in string operations. And 2 other special usage of instruction that is defaults between most of the compilers is ESP register is used as the stack pointer. It always store the current index of a stack. And so when we use, for example, the push instruction to push something on the stack, it uses the ESP register. And EBP register is used between function calls as the base pointer to save the stack frame between function calls. And there are two other important registers that we don't have direct access to them by, for example, a move instruction. These are EIP and eFlag register. EIP register always store the address of next instruction that's going to be executed. So when CPU is going to execute some code, it's in every clock, for example, it checks the EIP register, fetch the next address, and continue its execution. So EIP register can be considered as the devil register for exploit developer, because when we can control our EIP, we can control the program whole. We can control the program whole execution and hack that program, for example. And EIP register, as mentioned, cannot be manipulated directly, but there are some special instructions that used for directing the control programs that change the EIP registers. For example, when call instruction is executed, it changes the EIP value, and there are also some other instructions, JMP, write, IROT. And there is another register, eFlag register. eFlag register is used for values, is used as a bit storage for various flags, and it has some kind of backward compatibility with the previous 16-bit systems. There are various flags in the eFlag register that you can read more about it in the Intel specification, but some of them are most important for us. For example, ZF register is used for is set when the instruction has the result of 0. These flags are used mostly for conditional branch instructions like JE, JZE, and like this. Go through the instruction format of X86 assembly. Every instruction of, first of all, instruction format of X86 assembly is some kind of variable size instruction. So an instruction of assembly can be 1 byte or, for example, 4 bytes. This system is not a static size instructions. Every instruction of X86 assembly contains an opcode and 2 optional destination operand and a source operand. They are not, of course, so optionals, but I call them optionals because in some instructions we use both operands, and in some instructions just one operand, and there are some instructions that has no operands. For example, the ret instruction doesn't have any operand. It just fetched the return value from the stack and jump to it. So every instruction can have 0, 1, or 2 operand. There are three kind of operands for assembly instructions: register operands, immediate value, and memory addresses. Registers are previously defined and used as their names. For example, EX register, IX register. Here you can see source operand as a register, and here you can see a destination operand as EX register. And here you can see a format of some immediate value in this purpose as a source operand. Of course, immediate values cannot be used in, for example, move instruction as a destination operand, because you cannot write something like this. But there are other memory address operand that is defined by the bracket letter. Well, X86 supports various kind of instructions. For a full reference of the whole X86 assembly language and instructions, you can see the reference in Wikibooks X86 assembly, as linked is here. There are various instructions in X86 that if you know more of them, you can, if you memorize the important one, you can reverse engineer. You can be a faster reverse engineer sometimes. Data transfer instructions like move, XCHG, stack, arithmetic, binary, comparison, floating point, control flow, and such type of instructions that is available through X86. But we covered some concepts of some theory concepts, of course. We will go to our lab to see the debugger and lab. Here I prepared some lab that this lab will be available for students that consist of our needed tools, of course, and of course there are other lab, a Windows 7 lab that the other lab is the same as this Windows XP lab. So we are going to see what we have in lab. In this lab we have a folder called lab. In this folder you have you can see every material that is needed for that chapter. For example, chapter 1. As you see, it's free and it's just have a POC file because we are going to exploit this POC file step by step in next stages. And after we exploited that POC file, we will have some other files as exploit.py, for example, for every chapter. And we have a vulnsoft folder that consists of the vulnerable software that we are going to exploit in next part. Of course, all of the softwares are available on the internet, but for the sake of simplicity, we made them here. Of course, all of these softwares are installed in this lab, so you don't need to worry in installation of them. And there are some stuffs that some utilities and tools for exploitation will be placed here. Well, let's start some working with debuggers as a kind of review. We have Immunity Debugger here. Immunity Debugger is a well-known debugger that can be considered as a Python-supported OllyDbg debugger. It's the same as OllyDbg, but it has Python support, and Python support and some automations can be more helpful for exploit developers. This is the reason most of the times pure reverse engineers use OllyDbg, but exploit developers use Immunity Debugger. And here we can debug a program in two ways. We can debug a program by opening it under the debugger. For example, here I'm going to debug the calc program, for example, the famous calc program, of course. When I load it in the Immunity Debuggers, it loads the program and pause at the main function of that program. And when I click this continue button, the program calculator will be open, and I can debug it, for example. And when I say pause, the program pause at the current thread, and you can see the threads, for example, in memory, as I mentioned before. Every virtual memory have some threads. You can see, for example, here a stack of thread, and here another stack of thread, and you can see list of threads here. The calc program have two threads, and the thread that is highlighted as red is the thread that we are paused in. And you can see also the mapped executables here as image type. And there are some mapped files here, as I mentioned before, and some private memory region or memory pages. These private memories are used as the dynamic allocations. And you can see here in this column the permission of every of this page. As you can see, for example, the text segment of every module is a read-only memory. You cannot write to the text segment of a module, a running module, of course. Well, very important concept of everyone working with debugger is the concept of breakpoints. For example, when we pause at the current, for example, we can see that next time I push a breakpoint in this point, for example, here. And when I run this program, as you see, the program paused at this breakpoint, and I can use the single step to pass this breakpoint. I mentioned before that I can use the open to openf executable for debugging. Also, another method is to use the attach. Most of the time I use the attach because some programs have different behavior when used with the open. So you can also attach to a process for debugging. As you can see, I can attach here, and there is a short key for every operation in Immunity Debugger. It is recommended for everyone that use the Immunity Debugger to know these shortcuts. For example, I use Control F1 key to use the attach. It makes you more faster. And here I have the CAD program to attach with. So I can now debug the CAD program in this mode. And there are various windows in Image Debugger. For example, the memory windows, that is the whole virtual memory, the executable modules, that is a list of all loaded modules in this process. The P can be used for threads. The color stack window, that when we pause at some process, for example, when we pause, you see that we will have a color stack of the program until this pause. The exact learning of Immunity Debugger is not part of our course, so I let it to the students. If they know how to work with Immunity Debugger, is good, and if they don't know, it's better to learn it more, for example, in other courses like reverse engineer, or use the materials in the internet to overcome these pre-requirements. And Immunity Debugger is good for some exploitation purposes. For example, when you are debugging some Microsoft binaries, when you are going to exploit some Microsoft executable, WinDBG is more helpful because of its design for Microsoft debugging. It supports various things like symbols and various data structures that we can use in our debugging. We will cover WinDBG concepts when we headed to our next chapter. But here I just run our WinDBG, for example. as you can see, I have a custom layout for my WinDBG program. There are other various layouts available via register key in the internet, and you can also make your own custom layout for your WinDBG program. And there are other tools in this lab. For example, we have the whole sysinternal suite here. Some of the applications of sysinternal is very useful for our purpose. For example, the Process Explorer application is very useful in some exploitation purpose or vulnerability discovery purpose. Because you can get more information from executable without debugging. It's very fast. For example, here we can see the DLLs of any module without the need of, for example, debugging it. And there is also, of course, some available columns for more cool things. Here you can see. Here we can see the base address of every module. Well, and of course, there is a hex editor in this lab, a simple light hex editor, that when we are going to exploit some file format, for example, in chapter 2, we are going to exploit some PCAP file that is the input of a Wireshark program. You can see that the hex editor can be helpful in analyzing and making some file format file. And there is a free editor here with highlighting syntax, Notepad++. It is very useful because it has syntax highlighting and some cool features that can be used in next chapters. Well, we covered some basic concepts and reviewed some things. Of course, in this chapter was not maintained for learning the whole basics. So everyone that know the basics, it's good, and everyone know the basics can learn it more through other course that dedicated to reverse engineering by ZDResearch, or they can use some available links and books. So good luck.